Welcome everyone. Today we're carrying on our study of optical phenomena, and in fact what we're going to look at is the photoelectric equation. Hope you got your heads with you. Let's go. So, have you ever thought about what factors determine the amount of current produced in solar panels? We know we want to move towards solar panels. It's a much greener energy source, but how do they know what current's going to be produced? How much current is going to be produced? Does it matter if it's really bright or overcast, or what are those things that determine the current? It's not just, let's hope we get enough current. We can actually work all of that out, which is important. So, we have looked at the nature of light previously. We've done a little bit of revision. We've looked at what the photoelectric effect is. So today we're going to spend time on the equation. Photons, these are our keywords. Kinetic energy, we know what that is. We've used it lots in this year. The photoelectric equation. So, the photoelectric effect, remember, we need to know what the threshold frequency is. So we're going to look at that again. We're going to look at work function, because that's quite important. We're going to look at photons. Now, this is all things we've done before, okay, and how they affect the photoelectric effect. Threshold frequency, remember, is the minimum frequency of radiation. So that's any part of the electromagnetic spectrum, usually referring to light, at which electrons will be ejected from the surface of a metal. Please don't forget out the word surface here, because the photons only hit the top of the metal, okay? So it's the surface electrons that are going to come off. It's not like the photons go all the way into the metal and then eject them. It's the ones at the top, okay, because those are easy to get out. Work function is the minimum energy that an electron in a metal needs to be emitted. So the electrons go, I'm only leaving if you give me enough energy. Give me enough energy and I'll go, but there's a minimum. If you give me more energy than that, we're even happier. So we're going to look at what happens when we give them more than the minimum energy. A photon is the name given to a quantum of energy when the energy is in the form of electromagnetic radiation. That just sounds really complicated, but really we call light particles a photon. We discussed that before when we did the photoelectric effect, the fact that it shows us that light is both a particle and a wave. When we're talking about light as a particle or any part of the electromagnetic spectrum, we call it a photon, okay? And that photon, that particle, has a certain amount of energy, and that's what we're trying to harness. We've seen this equation where E equals HF, E being the energy of the photon, F being the frequency, and of course H is Planck's constant. And before you go, but we don't know Planck's constant, it's okay, you don't need to know it, it's given to you. So, let's see how all of this becomes the photoelectric equation. Whew. Now everyone's just going, oh, this looks horrible. It's really not, okay? E, okay, I didn't write all of this in. This is the energy of the photon. So this tells me how much energy the photon has. I can calculate E by using HF, which is what we just showed you. But we've got to remember that the wave equation says to us that V equals F lambda. So if I don't have, well, first of all, we're looking at light. So we very specifically know the velocity of light. It's the same, so it's c. C is the speed of light, which is 3 times 10 to the 8 meters per second. Also, don't stress if you don't remember that. That's also on your information sheet. But if I want frequency on its own, frequency becomes c divided by lambda. That's all I've done here, is in place of f, I've put c over lambda. So this first part of the equation is all the same thing. It's referring to the energy of the photon. Which version of it we use depends on the information we're given. WO is the work function. Okay? Minimum energy needed for the electrons to start to get off the surface of the metal. We calculate the work function by that equation, HFO, where FO, remember, is the threshold frequency. There we go. Yes. No, that's spelt wrong. Sorry, guys. There we go. Let's just spell it correctly for you. Frequency. There we go. Now it's spelled right. If we know the threshold frequency, it's the same as our threshold wavelength, so it's all the same thing. EK max, this is the energy that the electrons will have when they leave. If they have more, if the E is bigger than WO. But how do we calculate E? EK, or half mv squared. This mass is always the mass of an electron. And again, you're going, but we don't know that value. It's okay, it's on your information sheet. Don't need to stress about that. We need to learn how to use these equations. So, we're going to take a short break, and when we come back, we're going to look at current. I'll see you in a couple of minutes. Welcome back. Now we just need to do a little bit more theory, and then we're going to do an investigation, which will hopefully help this make sense to you. Okay, so we need to talk about current. When we look at the current that's produced, we have to look at the frequency of the light that's hitting the solar panel or the piece of metal. Okay? We then also need to discuss how intensity changes current. So both frequency and intensity, intensity means how bright it is, both of those affect the amount of current we get. Because what we need to remember is that current is the rate of flow of charge. So when we talk about measuring current, we're going, how many electrons are going to be moving per unit time period? That gives us our current, okay? So let's do an investigation. So we're going to investigate how frequency affects current. And I have a very nice simulation for you. So what we have here, okay, don't worry about the graph, is I have a situation where this is like the setup of a solar panel. These little squiggly lines are the photons. These blue little dots are our electrons that are moving. Don't worry about the voltmeter. What I need you to be paying attention to is the ammeter over here, the 0.8 amps, okay? First of all, if I change the frequency of my light, okay, so now I'm changing the frequency of the light, eventually, can you see, I don't have the threshold. So there's no current. I haven't given it enough energy for the electrons to move, right? That means no current on my reading. As I increase, I'm just going to increase it a little bit. No, still none. Okay. Still none. I'm going to move it again. Still haven't got any. Yeah, no, it's getting a bit faster. Still not any. Still not. And still, usually it's in the ultraviolet. Ah, there we go. I've now got current, a small amount of current. So I have gone past the threshold frequency, okay? We are ejecting electrons from the metal, but they're not going very fast. So what happens if I make this, I'm keeping the frequency the same, but I'm going to make the light brighter, okay? So, is that making, ooh, let's see. Did you just see the current got bigger? I made it brighter. How am I showing that I made it brighter on the animation? By showing more of the squiggly lines. That tells me intensity is the brightness. So intensity means that we have more photons, okay? It's like the amplitude of a wave. All right, so it's a bigger amplitude. It's the same color, same frequency, but there's more electrons coming off. So if you look carefully, the electrons aren't moving any faster. We haven't changed their speed. We've just simply changed the number, because now there's more photons. The more photons we get, the more electrons can be taken out, okay? And if I make it even brighter, the current goes up again. We'll make it to its absolute highest, and that's now 0.4, okay? Still quite a small current, but it is a bigger current. Why? Because there's more photons. Let's make it back to being quite dim, and let's increase the frequency, okay? I make it a higher frequency light. We haven't changed much with the current. Let's make it even higher. Now you can see just by increasing the frequency, I've got the same number of electrons coming off as I had just now, but my current is now increased. That's because my electrons have more energy. So they're going to be able to move faster. And the faster they move, the bigger the current, because the current is charge passing a point per unit time. They're moving faster, we'll have more charge in the same time periods. If now I make it brighter, look at that. Big change in current, big change, because we already had a lot coming off. If I make it even brighter, I can even get it to 1 ampere. Okay, and if we go right to the top, this can go up to 1.6. The electrons are not moving any faster. We just have more of them. So we go back down here, and if I switch the light off, well, no current. That's fairly straightforward, okay? Let's go back to 1. Let's make it a much, so we're in the ultraviolet light. Let's make it as high as we can get it. Even before I change the current, you can see that those single little electrons that are coming off are moving much faster. They've got a lot of extra energy, which is how the photoelectric equation helps us, because we can calculate how much energy they have. If now I increase the intensity, we can actually we can get a very high current. Okay, so the more intense it is, all right, the more current we get. So when we look at things like solar panels, that's what scientists look at. They go, what is the threshold frequency of the metal we put in the panel? Then they go, and they control the current also by the rest of the circuit, which we're not going to worry about, okay? Then they've got to look at how much current's going to be produced when it's overcast. How much current is then produced when it's very, very sunny. And it all depends on what your solar panel's being used for. Because remember, some solar panels are used to charge batteries, which then kick in when the power goes off. And some solar panels produce an electric current, so you don't need to be connected to the electricity grid. It all depends on what those panels are used for. We need to take what we've seen here and look at it in terms of the equation, okay? So let's go back here. When there's a high frequency of light, the photons have more energy. That's what we just looked at. The photoelectrons, now this is not don't get upset about that word. I've just spoken about electrons. They're still electrons. We just call them photoelectrons because a photon kicked them out. They're still electrons. They haven't changed being electrons. High frequency, photons have more energy, so the electrons have more energy. We get a bigger current. When we have a low frequency, the photons have less energy, so the photoelectrons have less energy, and so there's a smaller current. It's fairly logical. You saw that. When it was a small frequency, we only had 1 or 2 little electrons coming off, and they weren't very fast. So small current. We've done that. Low intensity, make a note for yourself that intensity is brightness. I do want to show you just one thing quickly on that note. If we go back here, okay, and we go below the threshold, no electrons are coming off here. I need you to see something. Even if I start here and I keep increasing the intensity of the light, it doesn't matter how bright I make this light. It makes no difference. If the photon doesn't have that threshold frequency, if our photons don't have that minimum energy, we can make it as bright as we like and nothing's going to happen. So the intensity of the light will not make the electrons come off unless they were going to. That's very important to get because they're going to try to trick you with that, okay? The intensity has got nothing to do with starting them to come off. It's all about getting to that threshold frequency, okay? It's all about the frequency for that. So, here we go. If there's a low intensity, that means we have less photons because it's not as bright. If there's fewer photons, now watch, it's not about energy now, it's ejected per second, and it's the whole concept that current is charge over time. When we eject electrons, it's a charge that's moving. So if we have less charge moving per unit time, current's going to get smaller, okay? Smaller current. If we have a high intensity light, that means it's much brighter. We're going to have more photons, which means we're going to have more photoelectrons ejected per second. We're going to have a bigger current. These are good ways to explain these questions when we get there. So let's put in context how changing current and frequency affects calculations, okay? First of all, when we look at our 3 equations, and we're really looking at this, whoopsie, maybe I should actually have a pen so it doesn't disappear. When we look at this equation, okay, and we look at E doesn't mention intensity. So these equations don't help us with intensity, okay? So they're not going to tell us anything about current from intensity. All we can do when we look at current and we look at questions where they change the intensity of light is we can simply say it's going to get bigger or smaller. These equations help me when I want to do the speed at which the electrons move, okay? When we are at a point where we have just met the threshold, okay, we just met threshold, those two values are going to be equal. So we're at the point where we've just met the threshold, and in fact we wouldn't actually get a current if we're just on the threshold, because if those values are equal and we go HF equals HFO plus EK max, if this value and that value are equal, when I take it over, if they're the same value, then my kinetic energy is 0. Well, if the electrons don't have any energy, they can't move anywhere. All that happens when we meet that minimum energy is literally the electrons do this. So the electrons, so there's my little electron. There we go. The photon comes along, hits it, and the electron goes, fine, I'll sit on the surface then. That's what you want to be. For it to move, to create my current, I need to go a little bit above that threshold. Okay, so I've got a frequency that's a little bit higher. All right, as long as there's some difference between those two, I can get some value for the velocity. The bigger the difference is between those two, the faster they'll go, which is what I was trying to show you. That the higher the frequency, the faster the electrons will move, okay? That's the important thing. And how do I know what they're going to move? Because of this equation. All right. Please be careful when we do these calculations, because sometimes they're just going to want to know the kinetic energy, and you're going to get so used to calculations where you calculate the mass, the velocity, that you forget. Remember as well, electrons are very, very, very small. The velocities they move at are very, very big, okay? So don't get surprised when you have velocities that are times 10 to the 3 and times 10 to the 6. It's okay. And remember, they go in short distances. It's not like I'm trying to move a human at those velocities. We can't move at those velocities. But electrons can, because that value is so very, 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 very small. Electrons can move extremely quickly. And we're okay with that. That's not an issue. Okay. Wow. So, just quickly, the mass of an electron is 9,1 times 10 to the minus 31 kilograms. Tiny. You don't need to know it because it's on your information sheet. Welcome back, everyone. So we've done some theory, we've looked at some animations, now we've got to do the calculations. And the only thing that makes these calculations scary is the size of the numbers, but it's really not that bad. So let's do some problems together. First one, the work function of silver, and just to remind you, silver is Ag. And you're going, but it's not chemistry. This has a little bit of chemistry in it. The work function is 7,5 times 10 to the minus 19 joules, which is fine. Show that the cutoff frequency, or the threshold frequency for silver, is about 1,1 times 10 to the 15 hertz. They're asking you to prove what the threshold frequency is. All right? So, I know what the work function is. This is WO. I need to prove that value. So I can't put that in my equation. we remember that the work function is H times FO. They've told me W, 7,5 times 10 to the minus 19. H is a constant. You don't need to know it. Look it up on your information sheet. Don't go, oh, I know this one. Look it up because there's lots of constants that you use. Okay, and this constant is 6,63 times 10 to the minus 34. And I want FO. So to get frequency on its own, I'm going to be going 7,5 times 10 to the minus 19 divided by 6,63 times 10 to the minus 34. Yeah, we're going to need our calculators. This is not a nice one to do in our heads. So we're going to go 7.5 times 10 to the minus 19 divided by 6.63 times 10 to the minus 34. And look what we get. We get 1,13 times 10 to the 15. The question was to prove that it's 1,1 or thereabouts. They said about 1,1. That's close enough. So we can go 1,1 times 10 to the 15 hertz. I'm happy leaving it like that. If I'd been asked to work out the threshold frequency as a calculation and they didn't tell us what to compare it to, I would use the extra decimal place. But because of the way the question's asked, we're happy with it like that. All right, electromagnetic radiation of frequency 3 times 10 to the 15 hertz is incident. Incident just means that it's hitting the sodium. Okay, that's all it means. On sodium metal, sodium being Na, the emitted photoelectrons have a maximum kinetic energy of 1,6 times 10 to the minus 18 joules. They want threshold frequency, FO. We need to work through what information we have here. So we know that the frequency of light we're using is 3,0 times 10 to the 15. They're telling me that the maximum kinetic energy is 1,6 times 10 to the minus 18 joules, and they want FO. So we remember that energy of the photon is work function plus EK max. But we don't have the energy of the photon and we don't have the work function. But we are looking at frequency. So I can use the second version of this equation where HF is HFO plus EK max. I'm not going to write it as a half mv squared because I know the value of EK max. Okay? So now we need to write in everything we know. H is 6,63 times 10 to the minus 34. F is 3 times 10 to the 15. That's going to be equal to 6,63 times 10 to the minus 34 times FO plus 1,6 times 10 to the minus 18. At this point, now it's a maths issue. You've done all the hard work, and here's where sometimes it gets a little tricky for you guys. So the first thing I'm going to do is I'm going to minus the 1,6 on both sides. I want to make it so that I can do this calculation in one step on my calculator. Because if I don't, and I do all the separate steps, then we tend to have rounding problems. And we don't want to do that. So I'm going to take the 1,6 over. So I'm going to have 6,63 times 10 to the minus 34, 3 times 10 to the 15. I'm going to minus the 1,6 times 10 to the minus 18. And we're not going to worry too much about the space, and I know it's horrible. I want FO on its own, so now I'm going to divide by 6,63. So this is what I'm going to get. 6,63 times 10 to the 34 minus 34, 3 times 10 to the 15 minus 1,6 times 10 to the minus 18, and I'm going to take all of that and divide by 6,3 times 10 to the minus 34. Now grade 12, sorry guys, now, if you have another way to do this, so if mathematically you can see another way to do this, you are welcome to do it. This is not prescribed. This is me trying to make it easier for you. I may not have, and also I don't need to see the maths, but this to me is logical. So we need to do this calculation. So the top of my fraction, in fact, I'll use the fraction for you. So there we go. We've got 6.63 to the minus 34 times 3 to the 15 minus 1.6 to the minus 18. So that's the top part of my fraction. Now I'm going to go to, I'm going to do it the way I like doing it. 6.63 to the minus 34 times 3 to the 15 minus 1.6 to the minus 18. That's the top part of my fraction. I'm going to divide by 6.63 to the minus 34, and I get 5,86. Well, that will go to 5,87 times 10 to the 14. I'm actually quite happy about that value, and I'll tell you now why. So my FO is 5,87 times 10 to the 14 hertz. I'm happy with that answer. This was bigger. This was times 10 to the 15. I needed this value, the frequency of the light I'm using, to be bigger than my threshold frequency so that my electrons have kinetic energy. If I got an answer here that was, say, times 10 to the 16, I know I've made a mistake. Because if this is bigger than, if this was times 10 to the 16, I'd end up with a negative somewhere here. And it becomes a problem because for my electrons to have energy, extra energy, kinetic energy, this value must be bigger than the work function. So that's quite important. So when you get to the end of your answer, always look at your answer and go, does that answer make sense? Does it work with the information I'm given? That's a skill we've got to learn, because sometimes we get to the end of the question and we go, I'm done, it's fine. But meanwhile, the answer doesn't make any sense with the information, doesn't make any sense in the situation. So you've always got to ask yourself, and I'm happy, like I said to you, because that's a 14, that's a 15, 14's smaller, that's not a problem, okay? So, one long question done. We are going to take a short break, and when we come back, we'll do a couple more questions. See you in a couple of minutes. Welcome back, everyone. Hope you had a good break, good rest, your brains are with me, and we're going to do some more calculations with all those wonderfully long numbers. But it's okay, it's a nice section. So, let's see. Here we go, the photoelectric work function of potassium metal, so what they're giving me here is WO, and it's potassium, so it's K, is 3,024 times 10 to the minus 19 joules. Ooh, they're doing something a little different. They're saying light of wavelength 360 nanometers falls on the surface of the potassium. So the first thing they ask us is, what is the energy of the photons? Secondly, what is the velocity of the electrons ejected from the surface of the potassium? So let's start at the beginning. The first thing, we know the work function. This is the problem that now we sort of hit a roadblock, because they want the energy of the photons. We know that E equals HF, but I wasn't given F. What I do know is that C equals F lambda. There's two ways you could do this. You can work out the frequency of the light separately and then put it into the equation. But I'm of the opinion, if you can only do one equation, do one equation. Let's make our life easier, less likely to make a calculation mistake. So, frequency is actually the speed of light divided by the wavelength. So I can go H times C divided by lambda. The first two are given, they're constants. So this is 6,63 times 10 to the minus 34 times 3 times 10 to the 8. Information given to us on our information sheet. Now we get to the fun part. I've got 360 nanometers. I can't work in nanometers. I have to remember that 360 nanometers is 360 times 10 to the minus 9 meters. You're going to have learned the conversions between micro, nano, pico, and milli in previous sections. You must know them, okay? This is not given to you, not at all. And in this section, our wavelengths are often given to us in nanometers, very, very small wavelengths. That means over here, I've got to go 360 times 10 to the minus 9. Great. We open our calculators, and we've got 6.63 to the minus 34 times by 3 to the times 10 to the 8. Now I'm going to divide that by 360 to the minus 9. And I get 5,25. I'm going to, because they gave me the work function to 3 decimal places, I'm going to keep that as 3 decimal places, okay? Just to be consistent. So this is 5,25. Oh, no. 5,525. There we go. It's always important to read all the numbers. Let's just check that I have written it right. Yep. Just as a side here, as I've mentioned before, you've got to look at your answers and say, does it make sense? These energy answers are always small. I have a constant that's to the power of minus 34. It is ridiculously tiny. So when this value comes out to be minus 19, in our heads we go, it's not a lot of energy. But for an electron it is. Because of how small electrons are, that's a lot of energy. So we're good with that, okay? And it's in the same sort of range as that one. So if this was significantly more than that, I'd go, there's a problem. Okay, so we don't need to stress about it. So now we know what the energy of the photons are. And now they say calculate the velocity of the electrons ejected from the surface of the potassium under these circumstances. You calculated the last question to help here. So we got that E was 5,525 times 10 to the minus 19 joules. We know that the work function is 3,204 times 10 to the minus 19 joules, and they want the velocity. Well, they've actually made our lives a lot easier because E equals WO plus EK max. We know E, 5,525 times 10 to the minus 19, WO 3,204 times 10 to the minus 19. The equation to calculate kinetic energy is a half mv squared. I'm just doing this in separate parts because I'm going to run out of space. So I'm going to quickly do the minus. So the 3,024 needs to go over. I've already got my answer. I'm going to minus 3.2044 to the minus 19. And I get 2,321 times 10 to the minus 19. So that's a half. Now the mass of an electron given to you on your information sheet is 9,11 times 10 to the minus 31. It's very small. Okay. I need to take this over. So V squared is going to be 2 times 2,321 times 10 to the minus 19 divided by 9,11 times 10 to the minus 31. Definitely cannot do this in my head. So there's the 2,321. I'm going to times that by 2. I'm now going to divide by 9.11 to the minus 31. And I get 5,095, but that's V squared. I need V on its own, so I'm going to square root that answer. Okay, now I get a big number. And what I want to do is I want to put this into scientific notation. All your calculators can do that. So it's shift or not. This calculator can't. We'll just leave it as it is then, because that button isn't working. So it's 713827. Oh, that's a big number to remember. 713827. 713827, comma 67. That's B, meters per second. And if I did put it into scientific notation, which I really can do without my calculator, it's going to go 1, 2, 3, 4, 5. This is actually 7,14 times 10 to the 5 meters per second. 1, 2, 3, 4. Yeah. 7,14 times 10 to the 5. There's a reason why I wanted it in scientific notation, because the speed of light is 3 times 10 to the 8. Okay? This is fast, but it's not quite the speed of light. Okay? So be careful. If you get an answer here where the value you get is bigger than the speed of light, you've made a mistake. It can come close, but it's not going to move as fast as light. Okay? Because it's not light. We good? Okay. We get interesting ones now. So a metal surface is illuminated with ultraviolet light of wavelength, there we go, 330. Electrons are emitted, and then they go the minimum amount of energy required to emit an electron from the surface of this metal. They've underlined it, which means it's important, is 3,5 times 10 to the minus 19. First question, what you need to recognize for me is this. That's the work function, okay? First thing they want is the frequency, so C equals F lambda. C is 3 times 10 to the 8. We've just done the conversion, so 330 times 10 to the minus 9. We're going to divide by 330 on both sides. Let's do it here so you can still see the question. So 3 to the 8 divided by 330 to the minus 9. And 9,09. Oops, make sure you remember how to the 14. I was about to look in the wrong place. And I'm happy with that. Now just quickly. Now they want the kinetic energy of the photon emitted. Same as what we did just now, except, and I'm not going to do the whole calculation. This is for you to work out. This is essentially the equation we're using. It's the same thing as we've done before. I've worked out FO. I don't need this. They've given me that value. We've just worked out F, so we can put that in. They want the kinetic energy. We know this is 3,5 times 10 to the minus 19. And in fact, all we have to do is calculate Emax. We didn't need the velocity. So just be careful. This is why you needed the question we just worked out. This actually makes it not so bad. Okay? The next question is just, we're going to do this quickly. If the intensity of the light is now increased, what effect will it have? The kinetic energy, none. Intensity doesn't affect kinetic energy. Number of photoelectrons affected, it'll increase. Okay. No effect on the kinetic energy, increases the amount of electrons emitted per second. We've done lots of calculations. I'm hoping they're starting to make sense. Practice makes perfect. So that's it for today, and I will see you again next time.